I don't know. I just don't want to do like the video game industry stuff.
Okay. So we're moving on to chapter 2.
Do we get extra credit for being at 3 survivors? Just kidding. Do this.
You'll probably know
No, I'm just kidding.
We get extra credit by
because you're
getting
here.
extra help.
Yeah, exactly.
Yeah, it is nice to be able to actually talk to actual people instead of pretending like there's nobody here. It would be kind of
Yeah, it's just talking with people and they're like, it doesn't seem like you have to go at all. I'm like, well, if I wanted to Sabbath along, then yeah, sure.
Yeah. I don't know. I think it's. I understand we have people doing internships and stuff, but I think if you have the option to go, it's better because then you're kind of,
Yeah, I never liked online
it's
classes.
easier.
I don't feel like
I do bad in online classes.
Watching a video of me talking where you can't actually ask the person, ask me, it's like, I don't
Did
think
you
it's
end up
nice.
editing that video?
Anyway, I'll be editing this out of the video.
That's how I read that today.
I waited for him to get in this room before I went to the elevator.
But yeah, okay, so we're doing chapter 2. This chapter is all about processes, which we're going to talk about today. So, a process is an instance of a program being executed by an OS. So it's an instance. So like, Word is a program, and then you could have, I think that's not a great example. Let's do Java. Okay. When you use the Java virtual machine, you could have several instances of that, like running.
Yeah.
Yeah. And there's many examples of where we'll have instances of programs running. So, yeah. Here's an example. When a user opens a new application like a web browser or text editor, the OS creates a new process. The OS keeps track of each process using what's called a process control block. This has all the information about that process. This is some of the information, not all of it. It's going to hold the current instruction address, so what it's currently executing, the CPU is executing. The execution stack, so like if there's function calls and stuff, all of that. So if you have like a recursive algorithm or anything like that, it's going to have that. The set of resources used by the process. So do you using the GUI or using the printer or using all those things. And the program, what part of the memory, and the program being executed. That's the simplest part. Of course, the process control block is going to be running an instance of a program, so you need to know which program you're running. Okay, so in the book, they have kind of a walkthrough example, but this is mainly the important part here. So, for instance, when the user clicks Microsoft Edge, which no one ever uses, but okay. Let's do Google Chrome. A new PCB for Microsoft Edge is created. Okay, so we click on Edge. It's going to make this process control block, and then which actually points to the program and the resources, stuff that are being used. So this is the OS. This is the OS processes. The OS has a lot running in the background, and then this is actually like one of our user processes. So, and then this is Edge. So let me talk through this again. When we start the computer, OS starts up. It's going to have its own process control blocks for its internal things that it's doing. Then when you log in as a user, you're going to have some things that are running just for your login. Like credentials and all that. Yeah. So that's why we have a separate user process control block. These aren't super obvious to us, but they're always running, like these OS processes.
So is it like similar where like you make an account, like for example, like Windows 10 you can make an account and
Yes.
it's separate from a second, like a administration?
Exactly.
Okay.
Yeah. Exactly.
Account.
And like if this was a shared machine, like a server, then there might be one operating system. So like let's say you're logged on, so it would have all the stuff for your it would have something for you, and then it would have something for another user. And then you're going to have a process control block for like whatever programs you're running. Does that make sense? So let's do these activities. Bring this up. Okay. So, an OS uses a process control block to represent a process. I think this is pretty, yes or no?
Yes.
I would hope that we use a process control block to represent a process, yes. The process control block is created by the process when execution starts.
Trick question.
It is a trick question.
False.
It is false. The PCB is created by the OS, not by the process. So your OS is what basically you're interacting with to say, load this program. And so it's getting the program, loading it, having the process control block there. Okay. The PCB becomes part of the program being executed by a process.
True.
False. False. The PCB is an independent data structure managed by the OS. It is destroyed when the process terminates. The program remains unchanged. So the program's like the software, right? The PCB is like the running, it's basically telling you when you're running this software, what's happening with it, like what instruction are you on, what memory are you using, what other stuff. Two processes can be executing the same program.
Yes.
Yes.
Good. Yes, it can. Okay. Let's see. Did I want to do this one?
Let's do it.
Same.
I thought this.
You skipped it.
Yeah, I did skip it.
Says
It's confusing. Yes.
212 and 214.
Yeah, skip those. They're confusing. They don't help. We're not doing this. Okay.
What do you want to see? 214.
If you can do them, but they're.
I'm just saying in your PowerPoint it said 214.
Yeah.
Oh, did it say we do 214?
Yeah, it said
Okay.
212 and then it skips 213.
Okay, so we'll do this one. Okay.
This one's
This isn't super illuminating, but let's do it.
So
Should we do it? It's
response to the
confusing.
OS first, right?
Yeah, let's just do it. Okay. A process can be compared to the act of reading a book checked out by a student from the reserved book section of a library. The student corresponds to what?
OS.
Yeah.
The
Would
book.
it be the book? No.
CPU. That's why I'm kind of like not in love with this
And
analogy.
then
I don't think
it's
that
gonna
great.
be block, right?
The program corresponds to the.
The library reading room.
Let's skip around. Let's do it and then we'll go. The library reading room corresponds to what?
Well, we can't know until we do it too, because program's supposed to respond to something like OS maybe.
The memory.
Yeah, that's what I thought.
So what's going on? This analogy, that's why I didn't love this analogy. They're like, you're sitting in a room, the CPU is the student, the OS is the thing that's kind of like facilitating you being a student, right? Helping you out. The program would then correspond to a book. The librarian
Memory.
would be the memory, and then the checkout record is the PCB. But yeah, this is not great. Sorry.
Oh,
The
that's the
PCB
memory.
does a lot of other stuff besides being a record of like which, so whatever. It didn't really help us. Okay. A process is. Oh, let's go back to our slides. So I think that I will actually just say do this. You guys are my guinea pigs.
You have to make.
So I do that all the time. Okay. You're going to just do that one. Okay. A process is always in one of several states. The number and type of states vary between different OSs, but most will implement at least these 3 states. So you have to have these 3 states in the minimum. You can either be, the process can be in a running state, so that's basically the process is running. It has all the resources it needs, and the CPU is executing. That's what running means, right? The CPU is executing the program. If the process isn't in a running state, it would be in a ready state. This is when the process has all the necessary resources to run, but the CPU is not available. So it's like when you're doing the time sharing, it's sitting there ready. It could run, but there's time sharing going on, so it's just waiting for its turn to have the access to the CPU. And then third, a process is in the block state when the process is waiting on a currently unavailable resource. So it's blocked when it needs something it doesn't have access to, like in terms of like, memory or hard drive or something like that needs to be. Does this make sense? Okay, so let's do these. This is just a little walkthrough to make it even more clear. So we have 3 states. So a newly created process will be in the ready state. And then when the OS selects the process for execution, it's going to be running. And then when the process gets interrupted, like let's say to let another process use the CPU, it goes back to ready. And then when the OS restarts the process state goes back to running. So it's going to be usually going between those two. And then when the process, let's say, requests a resource that's not available, like if there's a file it needs and it's already open, the process goes to blocked. And then when that other, like when the thing it's waiting for releases the resource, the OS moves it back to ready. Okay. So you only can go, so there's some important points here. You can go in between ready and running. When you're in a block state, you don't go back to, the process doesn't go back to running, it goes back to ready to let the CPU know to pick it up or not. Okay. When it goes to running, you can go to blocked. You can't go from ready to directly to blocked, right? Because ready, you're not doing anything, it's just waiting. So it'd be like, that doesn't make sense. Questions about that? Okay, so the transition of a process, the transition from ready to running of a process P is caused by what?
OS.
Yes, OS. The transition from running to blocked of a process is caused by what?
The process itself.
Yes. Good. The transition running to ready of a process is caused by what?
Some other resource.
I'm sorry.
What's the first one?
The OS, sorry. The OS may wish to let other processes use the CPU. That's why basically it's the one that the OS is in control of that. Okay, the transition from block to ready of a process P is caused by what?
OS. Some other process.
So, P is waiting for a resource held by another process. So the release of the resource causes this transition. Okay, let's go back. Are there questions?
So what would be the some other process?
Sorry? Okay.
Is blocked is like if you're trying to read a file and it's opened by something else.
Yeah, it's just yes. Ready is basically like when you're just waiting for the CPU, and then blocked is when you're waiting for some other resource that you need, and you can't run without having access to that. Yeah. Okay. Some operating systems, they provide more complex set of states and transitions. These additional states may include the following. We could have a newly created process can be placed into a new state before the process is allowed to compete for the CPU. So instead of going right into ready, there might be like some intermediate state between being created and ready. And that might be the OS may want to regulate the number of processes competing for the CPU. So, usually you have like this number of processes and they're all being time shared. So maybe if you're, the OS might just have another holding place for processes it doesn't want to consider yet. They're just going to sit in. A process could be placed into a terminated state when the execution can no longer continue, but before the PCB is deleted. So this is all between basically. This is just like in the one we did before. There's no terminated. It's just kind of drops out and it's gone. But we could add this terminated state, and if you have that, the OS might want to examine, basically kind of check on something before it allows it to just stop running. Completely. Like maybe in this example, maybe there's some kind of error and the OS wants to keep a log or something like that. And then a process may be placed into a suspended state even though the CPU and all the resources are available. So this is kind of like a subset of being of a ready state. So the OS may want to stop a process to allow or suspend it to allow debugging or to regulate its performance. So that's just kind of like another. So these are other states that a process can be in. Go here, 11 and 12. Oh, did I skip something? I think that I skipped this. Okay, so we will just talk about this and I'll add this, I'm sorry. So the CPU is always running a process at a time. Multiple processes can share a single CPU by taking turns, so which we've talked about last time sharing. So a context switch is the transfer of control from one process to another. So basically whatever is being run by the CPU at that time, when we're running another program, there has to be some sort of like switch that happens. It's called the context switch. Each time a process stops executing to allow another one to resume, the OS has to save all the information about that stop process. This information is restored when the process again gets a chance to run. Okay, that is what the PCB is for. So when you have a PCB and you stop a process to run, like you put it into ready to have the other one running, you need to know like where did it stop. That's one important thing. And so that's one thing it's going to save is like the execution line. The information that needs to be saved is called the CPU state. The CPU state consists of all intermediate values held in any CPU registers and hardware flags at the time of interruption. One of the registers is the program counter, which determines the next instruction to execute. So all of basically the state of the CPU, which is like one of the things is the line you're executing, is stored. So when, in the process control block, so when you go back, you just can, basically the CPU can resume where it was. So there's like, it doesn't look like there's an interruption. So let's just go through this really quick. Okay, a process P is running. The current state of P is in the CPU, while P's PCB contains an out-of-date copy. Okay, so we need, now it's going to stop, so the OS interrupts P, so now we need to make sure that the PCB is updated, so it's got like where P was, so when we go back, we're good. So then, Q continues, and basically Q's execution is put into the CPU, and where it was executing is kind of given to the CPU, so the CPU can, run Q. And then once Q is switched, it saves Q state to the PCB, and then P basically gets its state put back in, and then, So what happens, the PCB, it doesn't continually keep track of where the thing's executing, because that would be a ton of work. That would be a lot going on. So whenever P, like a process, gets taken out of the CPU, its current like running state, everything about it that the CPU, that the OS cares about, is copied into the process control block, and then it's kind of shelved. Then you bring up the next process, it starts running. Then when it's taken down, all of its information is saved. So it's the information about where the program is in execution is only saved basically when it's taken out of the CPU. Does that make sense? Away from the CPU. It's not saved like constantly, like for the whole execution. So let's say you're running lines 2 through 11. And you get interrupted at 11. It's not going to say, oh, running 2, 3, 4, 5, 6. It's not going to save that in the process control block. It's just going to save at the, where it was when it got taken out, which makes sense. Okay. A context switch may be caused by the currently running process. Is that true or false?
Is it true?
Yes. The context switch may occur when the process P requests a currently unavailable resource. It can be, okay, there's like several things that can be true about this. So, can the OS make a context switch? True or false? The OS may want to let another process use the CPU. So this is when basically a process becomes blocked. Maybe it's going to go ahead and save its state in the PCB. And then when the OS wants to switch between things, it might save its state. Some other process queue, true or false? What do you want to say? It's one or the other. Nothing's going to happen in the future. False, yes. The OS can take the CPU away from a running process, or P can give up the CPU by requesting an available resource, but that's for these two. But some other process Q cannot cause a context switch for process B.
Can you
They don't know about each other. That's another thing too. So they can't really.
for number one, is it
Yes.
really the process deciding this, or is it trying to do something and the OS says you can't access it, so we're just gonna
Yeah, you know what? This is a good question. The context switch may occur with. Okay, so you're requesting something, so you're kind of blocked, so you store everything. I mean, to me, it's the operating system.
right?
It's
Because the
doing
process
that.
doesn't know anything about like the PCB, right?
Yeah. It doesn't. The operating system's doing all of this. So it's a little bit. Might take it out, some of it out. Okay, this one's pretty good. The PCB contains an up-to-date copy of the CPU state of a process P. When? When does this happen? When does the PCB become the most up-to-date? When P is running, when P is ready or blocked, or at all times?
When it's blocked.
So basically, the PCB only needs to know its current state of the process when it's either waiting, because that's when it got updated, when it was about to be waiting, just before it started waiting, or just before it got blocked. When it's running, it's not being updated, and then at all times would be, what's the other times? It's running, it's ready, it's waiting, I don't know.
When it's both.
Yeah, both. Okay, we will talk about this. This is one of the exercises for your homework. Okay, so we can talk about it. Okay. Where are we at on time? We're good. So that's the first section. We're taking that out. Just whatever activities are in here, you're kind of responsible for the, quizzes and tests if they're not in here, and then you don't have to know that material. So I'm going to take that out. That was coming up. Okay. Why processes? So why are we doing this process? There's different ways you could do. You could handle programs in an operating system. So we're going to talk about why we're using this kind of process PCB control structure. Okay. So structuring an application as processes allows independence from the number of CPUs and the type of CPUs. So we know a physical CPU is a hardware instance of a CPU. Multiple processes may run on one physical CPU using a technique known as time sharing. We've talked about that. Each process is basically given a virtual CPU. A CPU that the process assumes is available only to itself. Okay, so each process isn't aware of the other processes, and so they just think they have all the access to the CPU, and that's fine. And when we have structuring applications as processes, we have independence from the type of CPU. So a virtual CPU can be just an abstraction of the physical CPU, or it can be software that emulates the behavior of a different CPU. Okay. So this is just from the book. So with a different physical CPU, the virtual CPUs are not just illusions, but are implemented in software and emulate the behavior of the original CPU. The processes remain unchanged. So you could, have a process running on an emulator. I mean, you could have your program running on an emulator that's just kind of like mimicking the CPU you're expecting to interact with, and then that emulator is then, interacting with the actual CPU and its instructions. So it's like a middleware. And that's what a virtual CPU can do if it needs to. So this is C. What this one is showing is that each process thinks it has its own CPU, right? This is our actual one CPU, and each one thinks it has. If there were multiple CPUs, each process may actually have its own
It's
CPU.
like a kind of like thread, right?
Sorry?
Is it like thread?
This is like time sharing,
Okay.
which, I think that's a little different. That also does the same thing when you make threads.
Because isn't it like nowadays like it says like, well, you have an 8-core
Yeah.
CPU, well, processor inside of your CPU, like quad core, 4.
Oh, I see what you're saying. Yes.
Is this the concept?
Yeah, kind of. It's like along the same lines. And then this one is just saying, like, if you have multiple CPUs, each process could have its own CPU, which is always nice. Okay, because you get more computation power. So let's do these activities. Okay. So this one, let me just start this again. So in this picture, they're saying each process can have its own CPU if you have that in your hardware. And then the second picture, B, is showing that if you have one CPU, which a lot of our machines have, then the processes all share that, but they think they have basically their own CPU using this virtual CPU, concept. And then the third picture is basically saying the virtual CPU, another thing that it can do is be like an emulator in between. So if you write your software for one kind of processor and you're running on a different kind, it's kind of like a middleware. Okay. So in parts B and C of the animation, the physical CPUs have different instruction sets. The virtual CPUs have different instruction sets, or both the physical and virtual CPUs have different instruction sets. What's happening there? It's going to be the processes can run on different physical CPUs using virtual CPUs. Okay. So it has its own instruction set, and then maybe whatever we write has its. Okay, what is the maximum number of physical CPUs an application consisting of 3 processes can utilize? We have 3 processes. Let's say I'm like, here's a computer. You'll only ever run 3 processes. You have as much money as you want to buy CPUs. How many CPUs would you buy?
Like just one or
You
like
buy as many as you want. You could just buy one. It's going to be
It's just 3, right?
3, yeah. So the ideal thing would be each process has its own CPU. What's the minimum number of physical CPUs an application consisting of 3 processes can utilize?
0.
True, except it won't be able to run anything. We're going to just go with 1. Okay. On how, we should say, can utilize while still running. Let's put that on there. On how many virtual CPUs will 3 processes run? Nope.
each 3, right?
3, yes. Because a virtual CPU is like a
Oh,
CPU
okay.
given to a process. It's like a little thing that's like, okay, I have one CPU. It's like something, in between the actual hardware CPU and the process. Okay. The benefits of virtual CPUs. Independence from the number and type of CPUs provides several crucial benefits for a process. Multi-user support. So you can have multiple users, each represented by one or more separate processes, and they can share the same machine. So this is basically, remember when I showed you the graphic, and then when you start up the machine, there's like the OS processes, and each user has its process? This is what's happening. Okay. So that's multi-user support. Multi-CPU transparency. So an application written to utilize multiple CPUs will run correctly, though perhaps more slowly if only one CPU is available. So it can scale down or scale like up. And then portability. An application compiled for one type of CPU can run on a different CPU without being modified or even recompiled. Where do we kind of see this portability thing? What language? You guys better answer correctly. Yeah, they've only talked about this forever if you're at this point. So Java is a language that's really portable because of what? What is running when you have Java, when you're running? If you have a machine that runs Java, what's it got? What's it actually running?
The Java virtual machine.
The Java virtual machine, right? That runs on top of certain CPUs. So like the Java virtual machine, it kind of, that runs on like Linux, one that runs on Windows, one, or one that runs on Mac, and then basically you just give it your bytecode and it can run it. It's like that interface. Okay. So let's do 2.2.5 through 2.2.7. Okay. This is just showing you how the code is portable between different types of CPUs. So let's just look at this. Okay. A program containing a floating point add instruction is going to be executed. The CPU fetches and decodes the instruction. If the CPU supports floating point instructions, then the instruction is executed in the hardware. If the program can be executed without any changes on, the same program can be executed without any changes on a CPU without floating point operators, that would be implemented by the virtual CPU. The virtual CPU fetches the instruction and basically runs it. So there'll be some instructions that the actual hardware can run. There'll be some instructions that this virtual CPU layer will run. When the CPU with floating point operations is replaced with a CPU without floating point operations, what happens? Will the correctness of the operations change, or will the speed of the execution change? Is it faster to run on hardware or some kind of middleware?
Faster to run hardware or what?
Some kind of middleware software that's kind of abstracting whatever you want to do. Hardware always,
Yeah.
right? So
Because,
the speed will change.
Speed happens to like how much space you have in SSD, right?
Yeah. So the hardware is always faster. But when we write a program, some of the operations, any CPU that, there's different types of CPUs, obviously. Some CPUs support certain things that others don't.
Smart.
And so that's why we need that virtual CPU. Okay. Why then, so for instance, Dr. Eichholt has this cluster, and he runs a lot of deep learning, vector operations stuff. So he has CPUs that on the CPU do matrix calculation, like it's good at matrix math, because that's happening a lot in deep learning. So that's an example. So if you know you're doing something that's like, otherwise, I have a server that doesn't have those. I run the same operations, but that's happening like at the OS layer. It's happening here. So it's not going to run as fast. I don't do deep learning stuff as much as he does though, so it's fine. Okay. 3 processes are executing on 2 physical CPUs. Decreasing the number of CPUs from 2 to 1 will what? The speed of execution. Decrease, increase, or not affect. We have 3 processes, and there's 2 CPUs.
Does it not affect at all? I'm just guessing.
Nope, it will decrease. Okay, because they're all going to have to time share. So before it's like one's on, one's kind of split between the other 2. Increasing the number of CPUs from 2 to 3 will what? The speed of execution.
Increase.
Yes, it will. Increasing the number of CPUs from 3 to 4 will do what to the speed of execution?
Does not affect.
It doesn't affect because we
It's more
don't, just like got an extra processor. Yeah. Okay. Because we have 3 processes, they each have their own. Okay. An application running multiple physical CPUs must be modified in order to run on a single CPU.
No.
Why is that? Because of the OS. That's what the OS is doing. The OS is handling that for us. The main purpose of virtual CPUs is to improve the performance of a system. Will it improve the performance of a system to have a virtual CPU? No, not necessarily. Virtual CPUs allow processes to share physical CPU. Usually moves some speed. Yes. But it makes it easier to write code because we don't have to write for a CPU, just write for an operating system usually. And so that's why we have like Windows, Mac, and Linux things, but we don't say like whatever. I don't do hardware, so whatever all the different processors are, we just write for an operating system, not for the hardware. Okay. Questions. So what have we been talking about? Processes, process control blocks, virtual CPUs, which is another part of an operating system that interact with the process control block in the process. Okay. Let me go back to my PowerPoint. Okay. The modular structuring concept. So, an application can generally be divided into multiple tasks, each implemented as a process. So, using multiple cooperating processes instead of one has many important advantages. So, this is just basically saying when an application is written and run, it will be launched as separate processes a lot of times. Or if it's written correctly, you're going to launch it as separate processes. This is a good thing. You want to do this, not just one giant process. Important advantages. Each process can be designed and studied in isolation. Why would that be good? Why would you want your application you're writing to be in different processes, to have different processes?
So they don't like. I guess they use like CPU effective way where you can run multiple applications at the same time.
That's true. They might use the CPU more effectively.
So it just runs faster.
Reusability.
Reusability, good. A lot of these have a lot to do with why we just say to divide code up into functions or methods. Reusability. You can have. Sorry.
Like you can make sure this one process is really efficient.
Yeah, it's like, let's say you put your application in the world and then it takes forever to print something, like the driver's bit. You know, you could say like, oh, instead of having to wait through all of the thing and figure out where that code is, it's like its own, part, and you can just go and like focus on that. The implementation reduces the idle time by overlapping the execution of multiple processes, and different processes can utilize separate CPUs if available. So that speeds up the execution. Okay, so these are all good things about using several processes for one application. Okay, they love their metaphors. So here's a metaphor. Building a brick wall. This is basically what they're saying. You're building a brick wall. You have to go to the factory every so often and go get the bricks. So you're just basically kind of like, if there's no bricks at a certain time, you're stuck. But if you have a person that every so often is helping you and like bringing them to you, then they can go while you're working on them at the same time and get the bricks for you. And so it will actually end up being faster. Okay. And so that's kind of an example. And it's a good example. Okay. Do I want to? Okay. So, the two-process design. So if we have, let's say, a program that. Okay. A program that builds a wall. Okay. So here, the two process design reduces the number of switches necessary for the periodic checking of brick availability. We're going to say true. So we're going to have one process that's building the wall, and one process is just going to basically sit there and wait for whatever resource. So let me think of a better example. A file. Something with files. Okay, you got Word. Let's say you've got, let's just make the whole part where you're writing stuff be one process, you know, like where you're typing it. Of course, it's several processes in Word. You've got one process that is writing, saving to a file, okay? No, updating to the cloud. This is a better one. So the process that's updating to the cloud, that's its whole job. And so let's say so this process doesn't have to keep checking. It can do its own thing while this process keeps looking at the cloud to say, like, am I updated up there, right? So they can be doing separate things. And so this process is completely unhindered by this one. Does that make sense?
Yeah.
Okay. The two process design permits the mason and the driver to operate in parallel. So if you have two processes, can they operate in parallel if they're not dependent on each other? Yes, they can. That's the whole thing. Okay. I don't like their analogies. I'm like, do we want to even do this?
This one was hard.
I think we're going to skip this because the whole point of an analogy is to help you understand the material. If it's not helping you understand the material, then it's like kind of pointless. So let me kind of we're just going to do that. Just how you look at that. Okay. Questions about that whole thing? Okay. Maybe I think this is going to be section 2.2.3, right? Yes. Okay. Let me go back to here. So we have this process control block. We've kind of talked about what it does. Now we're going to actually really look into like what's in there, the data types, all that good stuff. So the PCB is the instantiation of a process. Upon creation, the OS assigns every process a unique identifier. This identifier, P, could be a pointer to the structure or an index into an array of PCBs. So it could be like an actual memory link that says like the PCB is at this address, or it could be like an array of PCBs where like the PCB object is loaded into this memory place, and then you have an offset. So it's like you start here and then you say it's like an index 2 or whatever. Okay. Here is a generic PCB. Let's look at all the things in here. We have a CPU state.
Mm-hmm.
Okay. What is the CPU state? We already talked about this. Let's see if you guys are paying attention. CPU state, what is it? We talked about it in the last section.
Program, counter,
Yeah,
the
program counter, registers, all that stuff. Okay. Process state, what's that? I'll just make you guys talk.
It's running, ready, or blocked.
Yes, running, ready, or blocked. Okay. Or if there's there's lots of, but those are like the three kind of generic ones everything has to have. Memory. Okay. Describes the area of memory assigned to that process. In the simplest case, this field would point to a contiguous area of memory. In systems using virtual memory, which we'll talk about later, this field could point to a hierarchy of memory pages. Okay, scheduling information contains information used by the scheduler to decide when the process should run. The information is usually the process's CPU time, the real time in the system, the priority, and all that.
It's like they prioritize like which program should run.
Yes,
And
exactly.
I think we talked about it like 240.
Yes. Oh, you're talking about the, yeah. Yeah, it's basically, some processes are more important than other processes. And so at that point, you're going to need to know some information. Let's see. Real time, priority, that, like deadlines, if there, if it has to finish at a certain time, things like that, they need to be in there. Okay, accounting information. Keeps track of information necessary for accounting and billing, like the amount of CPU time or memory. This is going to be more for like, if you have like some kind of server that they pay for, like, the CPU, the time they're a CPU. Now on the cloud, you pay for your CPU time. So they're going to have to keep track of that. And like how much, memory. Open files. Keeps track of the files your process has open. Other resources. Keeps track of any other resources, such as printers that P uses and is using. Parents. Every process is created by another running process. The parent process of a process is the one that created it. It could be the operating system. It might be something else. So the parent records the identity of P's parent. Children. A child process is a process created by P. Process P is C's parent. The identity of every child is recorded. So a process might spawn children. So the OS has its own process that it can spawn, children. Then your like you have application, it might spawn processes. Okay, so all of that is in the process control block, and there might be more stuff. Okay, which PCB fields may change during a process's lifetime? Will the CPU state? May it change, or will it not change? What about time sharing? What's happening?
Okay.
Yeah, it's going to change. The process states. I have to remember, there's so many of these. Okay. Yeah. Okay, so are we going to be switching between running, ready, and blocked? Probably. Yes, it's going to be happening. Because of time sharing and different things. Resources they're all sharing. Open files. Will it not change, or may it change?
It'll change.
Let's see, Jim.
Did you say may change? Will change? Okay. Parents may change or won't.
No.
It better not. That's going to be a problem. Children may change or won't.
If
It wouldn't, right? Because the parent
Yeah.
wouldn't change.
The parent won't change for
Because
sure.
children is directly related to the parent, right?
Well, let's see.
it's like we are the parent now.
So the reason it's going to change, like, okay, if your parent's the operating system, okay, whatever your parent is, either you have a parent or you don't. That's the thing.
If the parent stops running, do all the children stop running?
Yes, they're all. Yes. So it's like, yeah. So your parent won't change ever. It's not like you're going to switch from one parent to the other. But if you have children, because a children state, yeah, it can like spawn a process and
die.
then stop. Yes.
Some new ones.
Parents die too, but not in operating system.
The
So,
whole
yeah.
family dies.
It's not, yeah. The parent-child analogy does not work with like actual people. You have to think about it in terms of operating. Yeah. So the parent will always be there. The children, because it's like spawning the children, it can like they can stop running. Make sense? Okay. Indicate which PCB fields may change while a process is running. Okay, so this is just when it's running. Will the CPU state change when something's running?
No.
No, remember that doesn't change until you go to blocked or ready. Will the process state change when something's running?
No.
Right, because it's in running. So
Because it'll only change when you stop it, right?
yeah, and then it's in stop. So it's just like open files. When it's running, can the open files list change?
No.
No, it can change because you can like it can be open and closing files.
Does-
Oh, but I see what you're saying. Like if it's a PCB.
Yeah.
That's a good question. So now I need to go look. Is the PCB, is the CPU state the only thing? I think it's the CPU state the only thing that doesn't get changed because it's changing so often.
Uh-huh.
But the open files is like something that's not changing as often. The parent, will the parent change? By the way, there won't be like super tricky questions on the test, so it's just gonna be really obvious things. So I'm not gonna.
No,
Some of
right?
these are a little bit like weird. Parent, will it change while the thing's running? It never changes.
Yeah.
So that's,
And then children will change.
it could change.
Yeah.
Okay. Here's our PC data structure. So all this is saying is different ways that you might want to represent these different parts of the process control block. This is going to talk about C. This would probably change. Okay. The PCB is implemented as a heterogeneous data structure. What's an example of a heterogeneous data structure that we use in Java? It says it right there. Guys!
Yeah, I'm sorry. I don't
Okay,
know what heterogeneous
I'm sorry, you don't know a
is.
heterogeneous. Okay, I'm sorry. A heterogeneous data structure is one that can
First.
have different types of data in it. Like it might not all be integers or all be doubles or
Like,
all be like an array is not. It's a homogeneous
Just
data
an
structure.
object.
Yeah, any type of object.
Yeah.
You can put whatever you want in there. Like you can have all your attributes and they can be different things, right? But if you had arrays can, but there are several things, a lot of data structures cannot be heterogeneous. But an object itself is kind of, like they talk about a struct, that was like the thing before an object, you know? Was a struct where you could put like different things in like the data structure. Now we just have objects, so we don't need structs anymore. That was kind of just like the little, that was kind of like the, something that was created because it was needed, and now we have the full-fledged thing. Okay, here's an example. CPU state. Okay, so actually, let's see. A CPU state could be a set of integers. A process state could be an integer or a character. So it could be like 0, 1, or 2, or it could be like, you know, U for running, R for ready, you know, something like that. It can't be a bit because there's more than 2 states. Okay, a memory would be a set of pointers. Scheduling information could be a set of integers, like different priorities and stuff like that. Accounting information could be a set of integers. Counting keeps track of information. Yes, that makes sense. Okay. Open files, linked list, start of the linked list. Other resources, start of a linked list. A parent could be a pointer or an index into, you know, an array of processes or PCBs. Children could be another linked list. We are going to skip these because we're not working in C, and these are kind of like C dependent. Let's see, did I say we would do 2.3.5? No, we're not. Okay, so we're skipping those. Okay. The OS must allocate and deallocate process control blocks efficiently as processes are created and destroyed. This is really important. So there's 2 ways that are used to organize process control blocks. One is an array of structures. The PCBs are marked as free or allocated, which eliminates the need for dynamic memory message. So it's basically like you just have this big array, and then each one, it's like if it's assigned a PCB, it's marked as allocated and it has all the information. Otherwise, it's marked as free. So it'd be like you have, I don't know how many processes, you know, let's just say like it's a teeny little, you have like 10, obviously you're more 10. And then like you're running 5. So like the first 5 would be allocated and they're free. And they're marked as free or something like that. An array of pointers to dynamically allocated PCBs. The pointer array wastes little space and can be made much larger than an array. The drawback is the overhead of dynamic memory management to allocate a new PCB and to free the memory. Okay, so if we have allocated memory, we're using more memory, but it's faster. If we have dynamically allocated PCB, we're actually using less memory, but it is going to be slower. So we have to like find the memory, you know, the CPU's got to figure out where there's free memory and do all that stuff. Okay. We are going to do these activities and then we're going to have a break. So let's just do these. And then we will. Actually, you know what? Actually, yeah, let's do it. Okay. And here is just basically a little, like one of their demos. So here's the array. So you can do this within an operating system. We have an array of PCB structures. Each either has a PCB or doesn't. So, yeah. And it looks like, because I was thinking they're all going to be at the front, but I guess if you're doing all this, they're going in and out, you can't kind of keep them collected, so it's just going to be kind of like, you know, there. So there we have that. Allocating a new PCB involves selecting a free slot and filling with the entries. You don't need to go find the memory. It's allocated in this array. With an array of PCB pointers, each entry points to a PCB structure or is marked as free. To allocate a new PCB requires the dynamic creation of this new data structure, and then a free slot has to be located and made to point to it. To destroy a PCB, you just simply mark it as free. And to destroy a PCB with the array of pointers, it must be freed. The structure has to be freed, and then you mark it as free. Okay. So, the set of all process control blocks can be implemented as what? A two-dimensional integer array, a one-dimensional array of structures, or a linked list of one-dimensional integer arrays.
Would it be one-dimensional array? No.
Yes. Good.
Yes.
Yeah.
Oh, it's not a telltale.
Just say like, I knew it the whole time. Like, you gotta be better at bluffing. Like, yeah, I knew that. Yeah, okay. The fields of a PCB are of different data types, and thus each PCB can be represented as a structure. Okay, so this is what this is. A one-dimensional array of structures. That's what this thing is here. We can do that. Yeah. Okay. When process control blocks are allocated and free dynamically, the overhead of the dynamic memory management could be reduced by reusing PCBs of destroyed processes. True or false? What do we think? So basically it's saying instead of destroying the memory where we have the PCB completely and putting something completely different, like with different data and everything, we could kind of keep it there and then reuse it later once it's been made. Because it's got all the, you know, slots that you need and it's got all the I'm just going to go with true. Yes!
So
Could be reused.
So that would be like you start out with like one PCB and then maybe you get up to 5 processes and then you go back down to like 1.
Yeah.
But those 5 are still there, they're just marked as deleted.
Yes.
And then as you need them, you can just start reusing them.
Yeah, and then like you could have some sort of thing like if you really need them, you could write over them. So it could be kind of, you know what I mean?
So it's like lazy loading.
Yes, exactly. It can be like that. Reusing process control blocks of destroyed processes rather than freeing the data is more time efficient and also more space efficient, equally space efficient, or less space efficient?
Less.
It is. So we talked about this. I think there's one person from 3-4, I think just a few weeks ago, but most things in computer science are going to be trade-offs between time and space. And so operating systems is just another example of that. A lot of times it's either going to be save time or save space, but you can't do both. You can kind of like, you know. Okay, now we're going to stop, take a few minutes break. I'll be back in like 5 minutes or ish. Walk around with it. Let me stop this. What is mine? I am actually, oh wait. Okay. Okay. So, oh wow, that took longer than that. I'm sorry. I walked to my car to grab my keys in the car.
It's fine.
You're like, it's fine. It's what you need. It's like, okay. So, avoiding linked lists. Linked lists require dynamic memory management, and that is costly. So, Linux has pioneered an approach that eliminates dynamic memory management overhead of linked lists. So, instead of a separate linked list anchored in a parent's PCB, the links are distributed over the child's process control blocks so that each points to the immediate younger sibling and the immediate older sibling. The original two fields, parent and children, in the process control block are replaced by 4 new fields. So usually we have parent and children in, I guess, Windows and Mac OS. Now we're going to have in Linux a parent, which is just always going to be one pointer. A first child points to P's first child. Younger sibling points to the sibling of P created immediately following P. An older sibling points to the sibling of P created immediately prior to P. So it's basically like 2, 4, 2 after. Yeah, so it's just sort of like a basically it's a linked list or some kind. Okay. So let's just look at this really quick. So process 0 has 3 children. A child pointer points from 0's linked list to each child. Each child has a parent pointer to 0. Process 2 has 1 child linked to 2. So here's all this. Okay. So basically here we have 0, and then all of its children got to point to it, and it's got to point to all of its children, and this is kind of the traditional way to set up a parent child. In the list-free implementation that Linux uses, all children point to the parent, but the parent only points to the first child. So it doesn't point to all the children, but just to the first child. Instead of the separate linked list, all child processes are linked to each other, that's what this is, using the younger sibling and older sibling links. So they're not linked to everybody else, it's just the one created before and the one created after. To add a new child under this implementation, a new link is dynamically created to point to the new PCB, and the PCB is linked to the parent. So this is like the traditional way. To add a new child under the list-free implementation, only the older sibling is modified to point to the younger sibling, and then no dynamic memory allocation takes place. So yeah, so it's just a different way of doing it. It's supposed to be faster because there's just less, like, you're creating less memory. Also a little bit better with space. So I think that's me. And I was reading this, I'm like, this to me seems like it's using list, and this doesn't use list. So I don't like the terms they're using.
The one on the left is a linked list. It's the little orange and green, the little tiny blocks are the linked list.
I guess I just think of this as also a linked list of some kind. I guess it's just the way I think. I mean, it's not really, but I don't know.
It's like a doubly linked list.
Yeah, right. I mean, I see what they're saying because of this. Okay, so I guess yeah.
But it's also not, because like the linked list.
Because you can't get to every.
The linked list holds pointers to the PCBs, but that doesn't have pointers to each one.
So it's just basically, it's a little, yeah, I see what you're saying. I see. Okay. So this, yeah. So the list-free implementation requires how many fields in the process control block instead of 2? So how many do we have now?
4. Right?
4.
Yeah.
Yes. So parent, and then okay. So the list-free implementation has parent, child, older sibling, and younger sibling. The list-free implementation is more time efficient, less time efficient, or equally time efficient as the linked list implementation. What do we think?
Equally? No.
It's okay.
Less?
This is how we learn. No.
More.
More. The main reason for list-free implementation was to improve time efficiency by avoiding the dynamic memory management needed for lists. Because it takes time. You don't think of that. I don't either, like when you're, doing this, but it does take time to actually figure all this out for the CPU time. The list-free implementation uses less memory than, more memory than, or the same amount of memory as the linked list implementation. What do we think?
Is it more?
Yes. The linked list implementation needs 2 pointers for every child. The list-free implementation needs 2 additional integers for every child, but also for the parent. Assuming pointers have the same size as integers, then the list-free implementation is marginally less. So it's not a lot. But you're saving on time. So when between our space and time, we're going to save time, and it's not much memory, so it's better. Okay. The OS maintain. Okay, so let's go back to here. So this is all here. We did those. The OS maintains all process control blocks organized on various lists. A waiting list, so there's different lists that they're put into. A waiting list is associated with every resource and contains all processes that are blocked because the resource isn't available. So if there's a resource that everything needs, processes need, there's basically a list there that they're all put in to say they're waiting for this resource. Another important list is the ready list, a list containing all processes that are in a ready state and are able to run. The ready list maintains all processes sorted by importance, which is expressed by the priority value, an integer. The ready list can be a simple linked list where the top priority processes are more toward the front. And then the ready list can also maintain processes in like a priority queue, and there's just different ways you can do it. All kinds of data structures. Okay, so let's do these 13 through 15. Okay.
You can even do it on the phone.
Oh, that's cool. That's nice they made it. Okay. So here we have a ready list that's they're all used as a priority list. So a ready list consisting of priorities 0 through n currently contains processes at levels 0, 5, and 7. The highest priority level 7 is running. A new process at priority 5 is entered. Process at level 7 continues to run. When a new process is entered at a priority above 7, then the currently running process turns from running to ready, and the new process starts. So this is one way to do it. So the ready list, if you have more of a priority, if something is more important and it comes in, then it gets ran. Basically, the thing at the top of the list is what's being run. Otherwise, it's placed like in the about order of priority, wherever is free in the rest of the list. Okay. With a ready list implemented as a priority list, the range of priorities is N1 through N2, where N1 and N2 can be N1 equals 0, N2 greater than 0.
True.
Yes. The most common choice is to start the range with N1 equals 0 and choose N2 to provide the desired number of priority levels. So basically 0 through 7 provides 8 priority levels, which makes sense.
True.
Should N1 be 0 and N2 be 0?
It can be.
It could be. It's according to the way you set it up. It's according if you only have one priority.
It's true.
Yes. So if you don't have any priority, it can just all be one list. N1 less than 0, N2 greater than 0. Sorry.
No.
No, it's true.
That's what
Oh, it's true. Sorry. My brain's also not. I need to wake up. Okay. Depending on the implementation's needs, the range can start and end with any integer. So you could go from -5 to 5, and that's 11 priority levels. So basically, according to what numbers you pick, that's just kind of what it's doing. If you want to have a priority list, you can't have just one number because that's all the same priority. But you can go from negative to positive, 0 to whatever, like whatever you want to do, whatever it's set up. Okay. A single ready list could not be used with multiple CPUs, true or false? Can we use one ready list with multiple CPUs?
Yes, right.
We could. Yes.
We can try.
We can do it. So starting with the highest priority non-empty list, multiple processes can be marked as running in the ready list. So with 2 CPUs, the processes at level N and 7 in the above example could both be in the running state. So basically you just could have more than one in a running state instead of just one. Okay, here we have the exercises. I gave you 2, 3, 1, 2, 3, 2, 2, 3, 4. So let's go back to, we have plenty of time, so let's go back to 2.1 and look at that one. Okay. Let me. Okay, so have you guys worked on this? If you have not, have you or have you not worked on 2.1.1? Okay, so work on it a little bit.
Balance between the transitions.
It's
Yeah.
the first person.
You have to like build like the ship cycle under, right? But now you can just build everything off of this.
Okay, I see.
You get ready.
Ready.
It's like
Wow.
then you can have like your mind. You have the train. You
So,
can have, like,
first one is valid,
so then
A,
you can, like,
because you just go to the circuit, and if it matches, it's valid.
Sorry.
Oh,
Sorry. Okay, let's look at 2. Okay. So what did you think it was?
Valid, because it goes to new, which is possible, to the ready.
Yeah.
And then ready to suspend, which is possible,
Mm-hmm.
and then go to block, and then also block can go back to suspended, so it's valid, right?
Well, okay. There's one thing in there that's invalid. So it is, but what is it? What's the thing that's invalid there?
I think it is said if you go from like suspended to block, you have to go back
Yes.
to the thing you came from.
Yeah, so you have to know that you're blocked. You have to be in. You have to be running to know that, right? It seems like.
Well, it's going back though, blocked to back to suspend. So
So if you're suspended, you're not. You don't know if that resource is available because you
Okay.
haven't asked. So you can only ask when you're in running state. So you can only be blocked when you're in a running state.
I thought like
Do we
you
have to give reasons why it's invalid?
You do not.
like I thought you couldn't go from like ready to suspended to blocked. Like if you get to suspended, didn't you have to go back to where you came from?
Okay, if you go to suspended. Oh, you mean you have to go back to ready?
Like if you came from ready and you went to block, you have to go back to ready. If you were
Yes, that is
sus-
another.
if you were like blocked and you go to suspended, you have to go back to blocked. if you
Oh, I
go to
see. Block. Okay. Would you have to go back to ready? Okay, let me think. Ready, suspended. You go to running from suspended. You could go from running to suspended, so not necessarily. You don't have to go back. You don't. But the problem is you can only be blocked when you're running, because you're asking for something basically. To become blocked, you have to ask for a resource. So if you see anything that's like new to block, any of the things to block besides running, that is an issue.
Second one is valid. It's suspended. So now it's suspended, goes to block and goes back. And goes
Right,
back to
like
block,
here,
goes ready, and then run.
Yeah, run it,
Here.
go back to ready and block. Back to block.
What do you do then? You go there.
You go
That's
back.
valid, right?
It's if you hit start on that, which will last. It does say that.
This is nice and confusing. You know.
Can we start at suspended then?
This is kind of.
Yeah, it can.
It should start. They're just kind of showing you like a snapshot of some of it, not like it starts. So that can just be like in the middle of its state.
Yeah. So we just assume we started already.
So actually, I kind of told you the wrong thing. As far as if you're ready and you're suspended, you can be blocked. But if you're, I don't like this. There's no way I would ever ask you this on a test. Okay. If you're suspended and then blocked, you can go back to suspended if the suspension occurred in the block state. So that's really, it's not the suspended block, it's the ready suspended block is the problem. Does that make sense? So I didn't explain that well, sorry. So the ready suspended block is not okay. What about the second one?
I thought it was okay.
It is okay. That whole thing is fine. You can go suspended, you can be suspended and blocked, and suspended and blocked. The idea would be like you were suspended for some reason, then when you come back, you can't do anything still, and then you're suspended again. Okay. What about C?
Okay, C, running, block, ready, invalid.
Invalid.
Because you can't go ready to block, right?
Yes. Because of that whole
Yeah.
running, block, that whole sequence. And then number 4.
New, ready, invalid.
Yes, why?
Because you can't go back to new.
Yeah, because
Once
we're
you
only in the
start.
new state once. That one's pretty easy. Okay, let's go to 2.3 because that I want to talk to you about 2.3.1. I think there's different ways to set that up, but I'm just going to kind of show you this way because I think it's the easiest. And I'll let you know.
You want us to draw it? On
Yeah, it's going to be a word. You can take a picture of it or something if you want to draw it, like on a piece of paper. Okay. Okay.
Just draw it and one,
So I'm not going to fill out the whole thing, but I'm going to draw the structure for you. Oh wait, it has to be. Oh, you know what? Oh no, that'll show the whole answer.
Why does it say? Why does it say we have to do 2.3.1? That isn't that multiple choice one?
No, that's the one that we're doing.
I mean the exercise, not the
okay.
activity. Yeah, it's kind of confusing. Okay, so here we go. So we are going to have 4. Like there's the parent, the child, and then the younger sibling and the older sibling. So we've got like kind of a row for each one. And then we are going to then, let's see, how many processes? 0 through 4. So then you would have like 0, 1, 2, 3, and 4. Like this. And then, let's see, am I missing anything? And then you can either put the number of the process that fits this category, or you can put like, you can basically kind of think about, I mean, it doesn't really matter, don't really care. If there's nothing, you can put like nil. If there's something, you can put the number of the process. If they don't say, just put nil. So nil, if nothing, or not specified, Otherwise, put the number of the resource.
I mean, how big
Is it 4 by 5?
would be 5 by 5? Did you need names and everything?
Starts again.
So what's going to happen if we add another resource? I mean, another process. Not a resource. What will we expand?
If you're adding another process,
What do we add to this?
you just start filling in the 0 column. Or are we doing like a 5th process?
Yeah, you do a 5th process. Let's say if they, yeah. And then if you, these aren't going to change, right? Because you only have. So that's the idea. There's different ways you can do this, but that's just. Okay. See if there's anything else I want to tell
If
you.
you have another lines.
Is that all we need to do?
Yes, for that. There's 2 parts to that one though. The first one, basically, you're putting the number. You're just basically making the connections, and then the second part, you have to add a little.